Hello, everyone. How are you doing today? I see the strongest ones are here. I know it's been a very, very busy day for all of you yesterday. How are you enjoying Moscow? Everything good? Your thumbs up? I know that some more people are joining us, but we would like to, keep the schedule so that have been prepared for you today by the ICPC alumni. So I know that a lot of people are watching us live. So hello to the ICPC Live. You are doing a great job. If you're not following it yet, please follow ICPC Live on YouTube. And just a few announcements for you today. Like we will see the schedule for today. We will start with a wonderful talk from Ilya Rosenstein, the ICPC gold medalist in 2010, the founder of Stealth Startup. It's a secret startup, and if you have a chance, maybe you can meet Ilya somewhere around and try to find out what is that. And then it will be followed by a panel discussion organized by the ICPC alumni, and Jelani Nelson will be the one moderating it. I will introduce everyone on the panel. Right after that, we have another lecture on AI that free time. You will enjoy the city. The weather is really nice today. Moscow is welcoming you. And of course, you can stay here, enjoy the chill zone. We have a lot of game activities. We have the tech showcase zone where you can meet a lot of cool companies and you can attend some virtual events by those who couldn't be here physically. So please enjoy. And I would like to welcome on the stage Ilya Rosenstein and Jelani Nelson. So you will see Jelani today quite a lot because he will walk us through all the talks and all the speakers. So let's give a round of applause to Jelani. He is the ICPC University Alumni Chair. And let's give a very warm welcome to Ilya Rosenstein, and I will let Jelani introduce Ilya.
Hey, hi everyone, thanks for coming. I'm very happy to introduce Ilya today. I dug through some old interacted with Ilya online in June 2007. That's when he was still in high school here in Russia. He asked a question on a forum about balls and bins and the Chernoff bound, and I answered him. I think I was a grad student at the time at MIT. And then afterward, he joined Moscow State, where he did his undergrad, and graduated in 2012. And while he was 2012, and while he was there, he participated in ICPC and actually went to the World Finals in Harbin in 2010 and got a gold medal with his team there. And then after he graduated from Moscow State, he moved to Massachusetts and became a PhD student at MIT, which is where I was. I had already graduated by then, and ended up having the same PhD advisor that I had when I was a PhD student. So it was quite a funny coincidence that this high school student I first spoke to in 2007, we were on opposite sides of the world, and we were in the same program with the same exact professor as our advisor. While he was there, he did some really great research work on high-dimensional algorithms, high-dimensional computational geometry, especially nearest neighbor search. He also did really nice work in low-memory algorithms, so-called sketching algorithms, low communication algorithms. And he actually won an award at MIT called the George M. Sprouse Award, which is for the best PhD thesis in computer science at MIT. So he won that award when he graduated in 2017 with his PhD. And right after that, joined Microsoft Research in the theory group in Redmond, which is near Seattle. And he was there for some number of years. And he has since somewhat recently, left Microsoft and is at a new stealth startup, as Veronica mentioned. So I'll pass on the mic to, one other thing too. As I mentioned, he was a two-time actually ICPC alumni, once also for MIT in 2013. So let me pass it on to Ilya, and thanks again for coming to give this talk. Oh, you have a mic already.
Okay, it seems to work. All right. Thanks, Veronica and Jelani, for very generous introduction. My name is Ilya. I would like today to talk about relation between competitive programming and modern algorithms design. And specifically, the question I would like to address is, first of all, what is algorithms research? And in what sense doing algorithms research can be continuation of your career as like participants of this competition, or maybe some related ones. First of all, just to give you an idea what my background is. Again, it was mentioned a little bit before, but let me repeat it just in case. Basically, on the left, some things that I did as a programming competition. Some of the stuff I did in the research land. So basically, on the programming competition side, I participated both in high school and competitions and in ICPC. Specifically for high school competitions, I went to International Olympiad in informatics both in 2006 and 2007. And then for ICPC, I basically also participated twice, in 2010 in Harbin and in 2013 in St. Petersburg. And on the research side, basically, I started doing research while still being an undergrad in Moscow State University, where I studied mathematics. Then I moved to United States, basically to get my PhD in computer science from MIT. Then after a short postdoc in Columbia, I spent a few years in Microsoft Research, also doing some research. And around a year ago, I decided to switch gears a little bit and started my own company. It's very loosely related on some of the research that I've done before, but maybe small right now, so I'm happy to talk about it, but maybe offline. And this is our picture from ICPC 2010, and that basically. Okay, so what is algorithm design? What is algorithms research? Let me give you some basic idea what it is, and then I will discuss relations, similarities, and differences, and maybe also give some remarks, like basically what does it take to transition from, doing competitive programming to working on algorithms as a research career. So, okay, so the basics are very simple. Basically, algorithms research is pretty much like solving problems. So you basically take a problem, then you solve it, come up with a better algorithm for a problem that community cares about, and I will talk more about it a bit later. Then you need to write it up as a paper, and then this paper should be published in a good conference. Basically, in order to get published, it needs to go through some rounds of peer review, and basically that's it. So that's the basic unit of doing research. So you basically just, after you finish one paper, then you basically start writing another one. Maybe you do a few of these things in parallel, but basically mechanics are pretty simple. Okay, and what does it mean for an algorithm to be better, right? So as you know, there are things like, for a program, there are some things that you might care about. Amount of time that it finishes in, some other parameters. And as in programming competitions, the main objective function people care about in the research community is basically worst case runtime of your algorithm. So for example, for some problem, maybe before the best algorithm was running in time n cube, and then you improve it, and now it becomes like n square, and this is great achievement, and you publish a paper, everyone is super happy about it. In some problems, this measure might not. Maybe, your algorithm takes time n cube, but time it takes n cube, it might be some like pathological instances, input instances that no one really cares about. So then maybe you are trying to formalize. Maybe there is some set of interesting instances, or maybe there is something else to say here. But basically, there is one direction in algorithms which is kind of weirdly called beyond worst case, and you're trying to come up with some new frameworks to analyze algorithms, not just in the worst case sense, but maybe in some other senses. Like one naive thing that you might want to ask here is, what about random instances? But then random instances usually ends up being a bad question, because usually random instances are easy unless you define them very properly. And so then maybe you say it's like worst case instances maybe plus some noise, and maybe noise makes the problem easier. And there are like whole directions here. Again, I'm not going to talk much about it. But then beyond, like basically besides runtime, there are some other complexity measures that you might care about. Like one of them is space. For example, how much space does your algorithm take? Maybe if you kind of make your algorithm more space frugal, then maybe the runtime blows up somewhat. There is a trade-off here naturally, right? And again, space, you have seen in programming competitions, so your program is required to take no more than, I don't know what it is these days, 1 GB of RAM. But there are also some other measures. Actually, some of them we might see later in the talk. Let me not mention them right now. And final remark here is there is a flip side of coming up with a better algorithm. Sometimes you might want to, you know, maybe there is some problem that people really care about, that you try very hard, try to come up with a better algorithm for it, but then you fail over years many times, and then maybe you start having an ideas, maybe it's impossible to do better than the currently best known algorithm, and then maybe you might want to try to prove impossibility result, that maybe there is no algorithm for your problem that runs on time better than n squared, right, where n is the size of the input. Unfortunately, this is a very so basically, in algorithms, there has been lots of progress, right? So we know how to do many things. For impossibility results, there are very few results that are known. And honestly, they're not very strong. So most of them are very weak. And that's why people actually have something else here. Instead of just saying there is no algorithm for problem X that runs on time n squared, they have like reductions between problems. So basically, if this problem is hard, then this problem is hard, then this problem is hard, then this problem is hard. So it doesn't give you like unconditional hardness results, but it gives you some evidence that maybe your problem is hard or might be hard. These remarks apply to theoretical research in algorithms, but then of course there is a closely related field of applied algorithms, or experimental algorithms. It has many names. And that's maybe closer to what you guys are interested in. So it's, you know, like we come up with a new algorithm, then we analyze it, come up with some running time bounds, maybe space bounds or some other measurements. But then, like, ultimately, what matters is how fast it runs in practice, right? So that's why we even do this theoretical analysis to start with. And then, of course, there might be some nuances here, right? So maybe your asymptotic bound for the running time is better. So maybe you improved n cubed to n squared, but it's n squared times 10 to the 10 to the 10 to the 10 to the power 10, right? So maybe then this n squared will overtake n cubed only when your input size is more than number of atoms and things like this, right? So then you would like to know that or investigate it, and the field of applied algorithms tries to do it just by, you know, implementing some of the theoretically motivated algorithms and like running them on instances that we might care about. And here is a concrete example. Actually, I learned it from the blog of Mihai Petrashku, who actually also was doing programming competitions. In particular, he got gold medal at International Olympiad in Informatics long ago. Unfortunately, he passed away very young, but he was like extremely prominent researcher in data structures and actually in impossibility results specifically. And so here is an example I learned from his blog. So just to give you some concrete problem, I don't want to be just high level and give you some bullet points. So here is a concrete algorithmic question that you might want to ask. Suppose that you have n integers and you want to build a certain data structure, right? So what should this data structure do? Basically, the query for a data structure is just a segment on the line A to B. And your data structure, given such a segment, should return any number that is in this segment. So it's basically like very easy problem, right? So how would you approach it? So it's pretty easy. I disclosed the suspense. Anyway, so it's pretty easy to do things like, you know, like some segment tree or some binary search tree or something like this. In fact, you don't even need any trees, right? Because it's a static problem. You don't need updates. So you can just do binary search among your numbers and find, for example, a smallest number that is larger than A, then check it if it is smaller than B. That's it, right? Turns out that this is not the best you can do, and there is a way to do it in absolutely optimal space and absolutely optimal runtime. So you can actually get constant time, and you can get linear space for this problem. And this is not the most recent result, but it's fairly recent. At least it was done in the last of decades. So this is a paper from 2001, right? And if you think about this problem, it's actually highly non-trivial. And the data structure for this problem is highly non-trivial, and it uses many fancy tricks. So this is an example what like a good research problem might be, right? So there is a trivial solution for this problem, which takes linear space and logarithmic time. But can we get linear space and constant time? And this is an example of result that, yes, we can do it, right? In this case, there are no respective impossibility results because, you know, this is clearly optimal and there is no way you can do better. Okay, so before talking about more technical stuff, let me kind of try to answer the question, what's the point of doing all that? So why do we do algorithms research, right? And there are many answers to this. So the first answer is that there doesn't necessarily have to be a point in doing it, right? So why do we do science? Why do we do basic research? Again, there are many answers to this. But in my mind, the most compelling answer is that, you know, doing science is kind of like preserving knowledge, curating knowledge of humanity in some like, fairly structured and maybe distributed way, distributed among people. If we wouldn't be doing science, then, you know, there would not be, there would be less knowledge in the humanity to speak of. So basically, by just, you know, refining some ideas, by coming up with new ideas, basically we carry on this goal, right? But okay, so this is maybe a little bit too high level, but what else do we need algorithms for, right? So one obvious answer is that they might just be useful for some practical application. And when I say practical applications, I actually mean two things. First of all, it might be useful in actual practice, right? So for example, maybe like some company like Google or some other company needs some algorithm to improve their storage or to, I don't know, improve running time of the training of like some state-of-the-art AI model or something like this, and they, you know, go read some papers, try to find some good algorithm, and, you know, then implementing it and making, like, being happy because their revenue increased by some %. But also practice might mean something else. So it might be that, you know, like, you don't necessarily use your algorithm in actual research in some more applied field. So maybe you know, you build some system or you build some, again, AI model, machine learning model, and you use some algorithmic insight to, you know, make things faster, make things better, make things more robust, and so on and so forth. And besides just, you know, taking algorithms and applying them to something, another example how things might happen is just through transfer of techniques, right? So maybe some technique that you developed to create your new algorithm, maybe it would be useful after some rework for something else, something more practical, or just maybe for other algorithms and stuff like that. So let me now talk about similarities and differences between competitive programming and algorithms research. Obviously, there are many similarities, so let me start with them. First of all, like, one way to think about algorithms research, which I think is very nice, is you basically solve how very well trained in it. So that's why, you know, going and becoming a researcher in algorithms, it's a natural continuation of what you've been doing already for many years. Basically, if you do not just theoretical research but applied research, then it also means that you actually write code too, right? And maybe similar to what you're already doing for programming competitions, code that you need to write to do any serious research in algorithms, it's kind of like a throwaway code. So you don't need to, you know, like write many unit tests. You don't need to have like good engineering infrastructure. So it's kind of, you're basically, when writing code for research, you are doing what you're already doing, right? So you don't need to name your variables in any like nice name. Like no one really cares about that. So it really like transfers perfectly in that sense. And in general, I wanted to say that skills that you acquired, they transfer very well in doing well as algorithms researcher. And just like again, and I don't know, like if you go and see results of ICPC or maybe like high school programming competitions, and you start like Googling the names, actually many of them will pop up as like, you know, professor of mathematics, professor of computer science, researcher in some industry lab, and something like this. So you can go and see this for yourself. But my point is that skills really transfer well. So if you're doing well in programming competitions, then actually you have a decent shot at becoming a good algorithms researcher. And so similarities, that's it for similarities. So now let me talk about differences. There are many differences too, and that's why I'm giving this talk, just to kind of let you look at the field a little bit and to understand whether this is something you might be interested in or not. So first of all, that's probably the most important difference is that if you look at the set of topics, almost all these algorithms, I think there are some exceptions, but I think 5% of algorithms that you need to do well in programming competitions, they were invented before 1990. So long ago, like 30 years ago, right? And of course, there are two ways to think about it. So one is not so flattering for algorithms research. So maybe since then, nothing really useful was invented, right? Because there are no good problems were created. But actually, I don't think that this is the case. And when I show some examples what was done in the field in the last 30 years, I think it will be apparent why some of these things might not be useful for programming competitions, but they might still be useful in some other settings. And couple of very important differences. First of all, the biggest difference between research and programming competitions is that in research you don't know that the answer exists, right? So when you go to the contest and you see some problems, then you know that they have solutions. And actually, often it really helps. Just the fact that you know that the solution exists, you can try to reverse engineer it, try to think what it could be. I know I can solve this problem in 1 second and 256 megabytes, so it must be the case that, the solution should look like that, right? So there is nothing like this, right? So you don't know if the problem has an answer. Maybe there is no better algorithm for the problem that you care about, and, you're out of luck, right? So nothing is guaranteed. And it can be somewhat psychologically daunting, but also it doesn't allow you to do this reverse engineering thing. So it's really, you are on the frontier of human knowledge. And probably even more crucial thing is that even the problems that you should work on, they are not known, right? So if you go to the contest, you see 12 problems, you know that you need to solve them. That's your job for the next 5 hours, right? But here, problems are not known, and there is a tension here. On one hand, we want to find the simplest problem because, then we can maybe succeed. But on the other hand, you want to find some problem that community cares about, and the problem should be somewhat interesting and maybe complicated. And in general, it should be well-defined enough so that, you with your skill set can attack this problem and solve it in some meaningful way. And honestly, after spending a few years on this stuff, I would say that finding a good problem, that's probably the hardest part of this job of a researcher. In fact, you kind of think about it as joint optimization for problem and solution, for pair problem and solution. So you come up with a good problem and solution at the same time so that you make some meaningful progress, other people are excited about it. And another big difference, it's a very important one too, is that the difference in the time frame, right? So when you are in the programming contest, you have a bunch of problems, you need to solve them in 5 hours. So basically, you need to have this burst of creativity in 5 hours, solve it, and then you can chill. In research, it's not like that. In many cases, solving problem takes years. So I personally had this experience where I started thinking about the problem 5 years before I solved it. So basically, you need to be much more patient, and you need to, in general, to play the long game. So oftentimes it happens that, over these 5 years, you have some small insights here and there, and then at the end of these 5 years, they would be put together, and then you finally see the big picture, and that's a pretty pleasant feeling overall, usually. So now let me talk about topics. So basically, I don't want to keep the talk purely high level, so I want to show you some technical stuff. There wouldn't be too much of it, but there would be some bits that I want to show you. Basically, this is what happened. These are some of the things that happened in the past 30 years in algorithms research. Again, of course, the field is huge, and I'm obviously biased by my own tastes, but I just wanted to show you some nugget in each of these things. Actually, maybe not in all of these things, but in most of these things. So basically, I will talk a little bit about randomized algorithms. I will talk a little bit about approximation algorithms, sublinear algorithms, complexity, if you think about it as algorithms, and I'll explain what I mean, and non-stat computational models. So let's start with randomized algorithms. Again, I'm sure you understand the concept very well. I don't want to dwell on it too much. But the point is, most of the algorithms that happen these days in algorithms research are randomized. So there are almost no deterministic algorithms being invented these days. Again, I don't have a concrete data. That's just my feeling. Maybe I'm not really, maybe again, I'm biased somewhat. But I think it's pretty accurate, to be honest. And again, there are many things you can ask about randomness. One obvious question, is randomness necessary? So maybe, you know, like if you have some algorithm that is randomized, so it uses random bits, maybe we actually don't need random bits. And this is a whole direction in itself, like de-randomization. Can we make our randomized algorithms deterministic without much loss in efficiency? And the problem is pretty much wide open. There are some concrete things, like for example, there is a very simple problem called polynomial identity testing. So polynomial identity testing is just you have polynomial given to you in some way, like maybe as a black box, maybe as some kind of like formula or something, over, like for example, polynomial can be mod p, right? And it's of many variables. Think of some polynomial of 10 variables or something like this, and then you would like to know if it's identically 0 everywhere. So maybe I give you 0 polynomial, I mask it, maybe it's like x minus x, right? In fact, x minus x is 0, but you don't know it in advance. So can you test that your polynomial is identically 0? And there is a very simple randomized algorithm for this problem. You can just start sampling random points, and if your polynomial is not 0, it's not hard to show that it's non-zero almost everywhere. So using sampling, you can solve it trivially, but there is no deterministic algorithm for this problem. I mean, there are, but they are not efficient. So basically, there is nothing known of enumerating all the points and trying them all. So basically, one great open question in this field is try to come up with a good deterministic algorithm for polynomial identity testing. And in particular, solving this problem is required to understanding whether randomness is necessary at all. Okay, so for approximation algorithms, I'm not sure if you've seen this concept, but the concept is very easy. You know, you might have some problem that is hard to solve, but maybe it's not so hard to come up with an answer that is not too far from being optimal. So here is a simple example, and you will see in a second why I bring this example specifically. The problem is called traveling salesperson problem. Basically, it's very simple to state. I'm sure, again, many of you have seen it. You have n points, and there are some distances between these points, and distances satisfy triangle inequality, so it's some kind of like a metric space. And you would like to find a cycle that goes through every point, minimizing total length of the cycle. This problem, there is some evidence that this problem is hard to solve exactly, but turns out that it's not so hard to come up, for example, with a cycle that is at most twice times the optimal cycle. And here is how to do it. So actually, let me show you the whole algorithm. So you basically take your points, then instead of finding optimal cycle, you find shortest spanning tree, so minimum spanning tree of the points. Then, of course, it's not a cycle, so we're not done. So what we need to do next is we double every edge. And if you double every edge of the tree, then you know that the resulting graph has Eulerian Tor, right? Because all the degrees are even. So you compute this Eulerian Tor. Again, it's not a cycle because you can go through every node more than once, but then you can do this shortcutting. So basically, if you need to go to a node, but you've already been there, you just don't go, right? So you basically take a shortcut and create a final cycle. So why this is too optimal? Well, because minimum spanning tree is at most optimal solution. Because any optimal solution for your problem, you can rework into spanning tree by just killing one edge, any edge, in fact, right? And shortcutting also doesn't increase the cost because you have triangle inequality. So basically, if you double every edge in spanning tree, find Eulerian sort, and then shortcut, you will get solution of at most 2 times optimal value of the original problem. Okay, this is great. So we are twice as bad as the optimal solution. Can we do better? You can actually modify this algorithm and get 1.5 approximation. So let me show you how to do this. The problem with the previous solution was that we were too wasteful. We actually doubled every edge. Do we need to double every edge? No, because we just need to take care of the nodes with odd degrees, right? Because of nodes of the odd degree, we don't have Eulerian circuit. So what we can do instead, we can just compute minimum matching upon odd degree vertices, and then do the same thing as before. So now we have spanning tree plus matching. Now it has Eulerian circuit. We compute it, we shortcut it, we obtain the final solution. Why this is 3/2? Why this is 1.5 approximation? Actually, like for matching, you can reason that it's at most half of the cost of the optimal solution. It's kind of simple. I don't want to spend much time on it. But the question is, can we do better than 1.5 solution? And this was not known until this year, actually. So basically, this algorithm 1.5 approximation was known since 70s or 60s, like long ago, 70s, I think. But no one knew if you can do better. There was some partial progress, like for some instances that we can do better. If your distances have certain property, then you can do better. But in the full generality, no one knew if you can do better. And actually, in this year, there was a paper that shows that you can do better. So you can improve upon 1.5 approximation. But the approximation it gets is 1.5 minus 10 to the power minus 36, specifically. So how should we think about this result? On one hand, it's cool. I mean, we made progress, right? It's such a basic, such a fundamental problem with almost trivial algorithm. I mean, I don't want to say it's trivial because, you know, some real people invented it. But it's like simple if you think about it. Like, I'm sure if any of you would have gotten this problem and thought about it for like a few days, you would have solved it, right? But no one really knew if this 1.5 is the right answer. And it's pretty tempting to conjecture that this is the right answer. But we didn't know this before. And so it's cool, we made progress in fundamental problem, but the progress is by ridiculous amounts, 10 to the minus 36. Like, should we celebrate? You know, how should we think about it? I think the right way to think about it, you know, it's like a nice progress. We kind of took we put a dent on the problem, so we know that 1.5 is not the final answer. So this is proof of concept, and hopefully more research will happen, and we will understand what the true complexity of this problem is. And also, I should say that this algorithm is incredibly complicated. It's way more complicated than this simple 1.5 approximation that I give you. And in fact, this specific paper got a best paper award at one of the best conferences in the field. So it's a big deal, basically. And I give you this example just to, you know, show you one example, you know, something non-trivial but simple is possible. But until very recently, we didn't know if this is the final answer. And now we know that this is not. So some cool progress happened in the last few years. So now let me talk a little bit about sublinear algorithms. So basically, again, sublinear, it's a little bit loaded term, but usually when you think about algorithms, research specifically, sublinear algorithms means that you either, so you have some input for your problem, and your algorithm needs to make some decision about this input without reading the whole input. So maybe it would just probe this input in a few places, and then say something. Or maybe it can, read the whole input, but it's not allowed to store whole input, right? So we are very memory constrained. And this is a field I actually spent quite a bit of time in. I don't want to talk about my research. I want to give you some very simple examples of what's happening. But interesting thing about this field is that you can actually show that both, in many cases, it's not always the case, but in many cases, both randomness and approximation are necessary. So if you want deterministic algorithm, you're out of luck. If you want something exact, you're also out of luck. So you need to have both of these things to even get anywhere in this field. So that's why randomness and approximation show up very prominently. Let me give you some example. Actually, I think Jelani likes to give it in his general audience talks, and he does it much better than me, but let me nevertheless try. So the problem is called distinct elements. And actually, Jelani has a paper that kind of closes the problem in some regimes. Again, I'm not going to talk about Jelani's algorithm because it's very complicated, or it's at least much more complicated than what I'm going to show you. But he's an expert, so him about distinct elements if you want to know more. But basically, the problem is very simple. So you have very long stream of numbers. Numbers are from 1 to n, right? So you see this stream, and you want to figure out how many distinct numbers have you seen. So this distinct can be anywhere from 1, if all the numbers are the same, versus n, if you have seen each number at least once, right? And you need to kind of find some answer in between. So how many distinct elements have you seen? Turns out that it's not very hard, and I will show you how to do it in a second. You can actually approximate this number without storing everything. And not only you don't need to store all the numbers, you need to store very few bits of space. So you can get, which is polynomial in the log n, where n is the range of the numbers that you are seeing, over epsilon, where epsilon is your required accuracy. So let me show you how to do it. Again, I don't want to write the whole algorithm, but let me just give you some basic idea. So the basic idea is you have your universe from 1 to n, basically you need to subsample this universe. So you need to find a random sample of certain size. Again, what size should you sample? That's a separate question. Let's talk about it in a second. But basically, you sample. So you say that, OK, I'm getting numbers from 1 to n, but maybe I don't care about the whole range. I only care about whether my number is equal to this, or this, right? Of course, you start having immediately problems, right? Because how can you store set S, right? You are not allowed to even store S fully. Again, let me sweep it under the rug for a second. Suppose for whatever reason we can do it, right? So then if you sample the random set, then there is a following algorithm that you can run. Basically, you receive a number, and you just check if it lies in this set. And all you need to check is whether your stream of numbers intersects. So basically, if any number is hitting this set, and you just your algorithm outputs 0 or 1, right? Whether I saw something in S or I haven't seen anything in S. And why something like this is useful is because it gives you some kind of statistical test. Roughly speaking, the intuition is that if number of distinct elements was very small, then if you sample random S, then it's very likely that none of these numbers will be in S. You can actually compute this probability exactly. It's pretty easy. On the other hand, if number of distinct elements that you've seen is large, then it's very likely that some of these numbers will hit S. Again, you can do this computation. It's pretty easy. And now the full algorithm looks as follows. Basically, you start sampling these sets. So you need to sample sets of different sizes to kind of have this test with different level of granularity. So you sample set of size 1, of size 2, of size 4, of size 8, up to n. So you have maybe a logarithmic number of different set sizes. And then maybe set size, you also need to sample a few sets of this size just to kind of increase robustness of your test. But yeah, that's basically it. And now I promised you that I will talk a little bit about how not to store the whole set S. And there are two answers here. You can either use hash functions for that, or you can use pseudo-random generators, specifically tailored to sublinear algorithms like this. But basically, you sample set S in some implicit way, and whenever you receive a number, you need to check about this implicit representation. Again, how to do it is a bit technical, but maybe not so important for this high-level understanding of what's going on. And for this specific problem, both randomness and approximation are necessary. So if you want deterministic algorithm, you're out of luck. If you want randomized algorithm but exact, you're also out of luck. So you need both approximation and randomization, which I think is pretty cool. And actually, again, maybe Jelani would be a better person to talk about it, but actually, algorithms for such algorithms for distinct elements, they're being used in practice. Again, we can talk what this practice specifically is. But more generally, this algorithm was an example of what's called streaming algorithms. So what is a streaming algorithm? Streaming algorithm is what I've just shown you. So if you receive a massive stream of data and you want to process it in some meaningful way, but without storing the whole thing. So you store only a small, maybe either carefully chosen subset of your data or some kind of compressed representation of your data, such that later, after you process your stream, you can look at this compressed representation, which is very small, much smaller than the whole data, but still be able to answer something useful about your data set, in this case, stream of numbers. It's a very rich field. There are lots of exciting things going on. There are still many open problems, and there are some even basic characterization problems. You can ask, what problems in general can we solve in streaming, but very little space. And as I told you about distinct elements, but more generally also streaming algorithms are used in practice. For example, I know specifically how streaming algorithms are being used in certain databases. Before running your query, you want to get some crude estimate what the result of the query will be, and that's where you might want to use some techniques like this to estimate what would be the size of the output of your query, or something like this. Usually, the problems you encounter are much more complicated than the distinct elements that I've shown you, but it's just a building block. So let me spend a couple of minutes, or maybe even 1 minute, about just in what sense complexity is algorithms too, right? And I kind of mentioned it in the beginning, but So what is complexity? Complexity is when we want to show that something is complex, right? So in case of algorithms, it might mean that some algorithmic problem that you might care about requires some non-trivial amount of time. Like just to give you some example, for example, you all know what fast Fourier transform is, right? So fast Fourier transform is just evaluating polynomial on roots of unity. You all know the algorithm for fast Fourier transform that runs in time n log n. Can we do better than n log n? Can we actually have linear time for this problem? Actually, fast Fourier transform is such an important problem that if you come up with linear time algorithm for it, you probably just decrease amount of computation in the world by some non-trivial amount, right? So it's kind of, important to know if sparse Fourier, if Fourier transform can be done better than in n log n time, right? And we don't know. We actually don't know the answer. We don't know any better algorithm. We don't know any non-trivial lower bound for this problem. So nothing is known. The answer could be anything. Like people conjecture that n log n might be the right answer, but no one has any approach how to prove it even, right? So, and this kind of reflects the state of the field in general. We have some lower bounds, but for most natural problems that we might care about, we have exactly nothing. So of course we know that you can't do better than linear time because you need to read the whole input if you want to give the answer exactly, right? But that's about it. So people kind of usually think about complexity results in somewhat different way. Again, I briefly mentioned it in the beginning of the talk, but usually people think about reductions. So maybe I don't necessarily want to prove that my problem is hard, but maybe I want to prove that if some other problem is hard, then my problem is hard, right? So why do I care? Well, like if, for example, the first hard problem that I'm using as a basis to prove that my problem is hard, maybe if people worked on it for decades and don't know any better result, then maybe it's some evidence that my problem is hard. Of course, like you need to be very careful with such evidences because even for very important problems, if you estimate number of human hours that were spent on this problem, usually it's not such a huge amount. So you need to take these conditional hardness results with a grain of salt. But nevertheless, these conditional evidences are better than nothing, and people are much more successful in proving them than actually like proving some absolute hardness results. And like, how do we prove such a reduction, right? We just design the reduction. So basically, if we have some basic problem and we assume it's hard, and our problem B can be solved efficiently. If like this supposedly hard problem can be solved efficiently using Oracle for our problem, suppose we have some black box that actually can solve our problem, right? Then you can conclude that our problem is also hard, right? Because if it was easy, then Oracle would exist, and actually our reduction could be used to actually solve problem A for real, right? So that's why reductions are also algorithms. So in fact, like complexity results, most of the complexity results are just algorithms in disguise. So it's kind of like dual view of the world, right? Algorithms are algorithms, but complexity is also algorithms. Everything is algorithms, right? So reductions are algorithms, and some of them are very actually like complicated and non-trivial. But the point I want to make is that you haven't seen this in programming competitions, obviously, because even though these are algorithms, they are like non-existent algorithms because they assume oracles of the problems that are hard, right? So that's why it's not like directly useful, but it's still very important to show some limitations of what we can do. And let me talk a little bit about non-standard computational models. You write code for, actual computers, actual CPUs, right? And you write it in some programming language that resembles C++. It could be Java, C, Python, whatever, right? Some reasonable language like that. Maybe you don't write your code for CPU, but you write it for GPU or for whatever hardware like Google is putting out to train ML models, right? But by and large, all these things, all these models kind of resemble what's called a RAM machine, right? So what is a RAM machine? So it's some device with some CPU and with a memory, and you can do random accesses, you can read from memory, you can write to memory, you have some registers, and you have some simple set of instructions, right? So it's a good abstraction of computational models, of actual computational devices that we really need. But algorithms research sometimes is concerned about other things. So maybe I want to introduce some other model and try to understand how easy I can solve this or that problem in that model. And the most obvious example here is quantum algorithms. And quantum algorithms, again, I'm not going to talk much about what they specifically are. Let me just say that these are devices, actually, like quantum computers are devices that run on some principles from quantum mechanics. Again, if you don't know what this is, fine. But the point is, such devices were conjectured to exist back in the 80s, and people started thinking, and like people did lots of research and understood that if you had such a device, you can solve many problems that we can using quantum computers, right? So it became a big deal because, like factoring numbers is not just a mathematical curiosity. For example, there is some cryptographic primitives that are based on hardness of factoring, like RSA. If you could factor numbers efficiently, so if we could build a quantum computer efficiently, like we would break RSA, so it's like good to know thing, Efficiently, so if we could build a quantum computer efficiently, like we would break RSA, so it's like good to know thing, And until relatively recently, people were mostly studying quantum algorithms purely theoretically. There were no real devices. People just, sat down and think, like, I can solve factoring on a quantum computer in this time. Can I solve this problem on a quantum computer in this time, right? So it sounded almost like, somewhat strange activity. Why do we invent algorithms for the computer that doesn't exist? But actually, this work was useful because, first of all, it guided people who actually tried to build quantum computers. And actually, relatively recently, some progress happened here. We still cannot factor any meaningfully big numbers, but at least there are some devices. They are not universal quantum computers. They specifically are built to solve one specific task, but they can solve some task that we conjecture is hard to solve on a classical computer. So it's not a useful task, but it's at least some task. So we already have a proof of concept that quantum computers is a real thing. Now we just need to make them universal and scale. Of course, both of these are like extremely hard challenges, but some recent progress happened, and I think partially this progress was motivated by some purely theoretical research on some abstract model that like very few people initially probably cared about. And again, like quantum algorithms are like extremely hot and exciting field. I don't want to talk about it. I don't know much about it, admittedly. But I wanted to tell you like my little personal story. How like we needed to do something in a non-standard computational model, and how we transferred some technique from some other field of algorithms. Again, like this is not really a prominent discovery. In fact, the paper where we have this, it's not even the main result there. It's just like one, I think personally quite cute lemma or theorem, whatever. But I just wanted to show you because this example is fully self-contained. You can understand the whole thing, and you can see some example of some like relatively like actually very recent like modern algorithms research. So it touches upon this topic of computational encrypted data, which is an exciting topic in itself, but that's not what I want to talk about here. So basically in computational over encrypted data, you want to encrypt your data in some special way that you can do some computations on this data without decrypting it. So conceptually, you start with some input X, you encrypt it into encryption of X. Then you can rework this encryption of X into encryption of some f of X, where f of X is some function I care about. And the point is you can do this transformation without decrypting your encryption. And then after you compute an encryption of f of X, you can decrypt it and obtain f of X. And that's a very useful primitive for many reasons. Actually, specifically, this primitive is called fully homomorphic encryption. Again, I don't want to talk much about it. It's a very cool thing. You can check it out. There is lots of activity going on in this field. But we wanted to do some computation over encrypted data. But the interesting thing about it is that if you want to do it, you need to represent your function f that you care about, so the computation that you want to do, you need to represent it as a circuit. So what is a circuit? Again, probably those of you who have seen some electrical engineering, they know what circuits are. So basically, if you programmed FPGA or something like this, you have actually built circuits. But conceptually, circuit is a very simple thing. So you have some inputs, and then you can combine these inputs into some intermediate results and operations that you can use for combining them. Again, you can choose some set of operations in a meaningful way. For example, it can be bit AND, bit OR, bit not, something like this. And then the final outcome of it should be the function of your inputs that you care about, right? And at the surface, it kind of feels maybe it's somewhat similar to RAM machine, but no, it's actually very different. And the main reason is that you don't have memory. So you cannot do any random accesses. You are not allowed to write memory. You are not allowed to read memory. And you are not allowed to do other things. Like, for example, you cannot have if, then, else. I mean, you can have it in the circuit, but if you want to compute this expression, you need to evaluate both then and else branch. So you cannot just, depending on the condition, go into one branch, because circuit should be like static. So this can be seen as some kind of like non-standard computational model, right? And specific problem we needed to solve was just having array of n numbers, find k smallest of them. So it's a problem that is completely beaten to death in the classical model. You know how to do it, I'm sure. You can do it in linear time by just if these k numbers don't have to be sorted, if they can be in any order, you can do it in linear time by just, running quicksort, but having only one out of two branches, right? Then you find number that is exactly kth, and then you partition your array based on that. Trivial, but what about the circuit? Now I want a circuit. I don't want RAM machine anymore because I want to compute k smallest numbers in an array, but when numbers are encrypted in some way. So how to build such a circuit? And then if you start thinking how to implement this quicksort, you start seeing that this is not possible to do as a circuit, because you have memory access, random memory accesses. You have this branching when you kind of choose which quicksort call to have. So it's non-trivial. But first, let me give you an observation that we improved upon. So the first observation is that maybe you cannot have linear-sized circuit, but maybe you can have something kind of almost as good as that. And in order to do that, you need to understand how to sort numbers using circuits. And again, if you start thinking about sorting algorithms, they are not very useful to be represented as a circuit for roughly the same reasons: random memory accesses, branching, and so on and so forth. But actually, people invented a specific primitive called sorting network. Again, I don't know how many of you have seen it, but sorting network is precisely like circuit for sorting. So it's basically a circuit where like gates are just comparisons, and you have output, which is n numbers that were input in a sorted order. And designing good sorting network, that actually was a big deal for a while. And having sorting network of size n log square n is fairly easy. And then you can also improve it to n log n. So you can have sorting algorithm that works in n log n time, but that makes all the comparisons in predetermined order. So you don't have any like divide and conquer or anything like that. You just like compare some numbers in certain order, and based on the result, you know what the sorted order of the numbers is. But this n log n bound is actually like, it's a pretty tricky paper. It's from 80s. It's called AKS sorting network. And it's also impractical. It's a complicated construction with a very big leading constant. So in practice, people are using n log square n constructions. But in any case, at least like theoretically, we can get n log n sized circuit for our problem. In fact, you can do a little bit better and improve it to n log k, because remember, we only care about k smallest numbers. You can do some simple trick to reduce your complexity a little bit. But now the question is n log k optimal? Like, remember, in the usual RAM model, we have linear time, and now we have n log k time, right? Turns out that you can actually get linear sized circuit, but you need to modify your model a little bit more, and not just have a circuit, but have a random circuit. So basically, circuit that you produce should be randomized, but it should work with high probability for any given input. And here is how to do it. It's actually the whole algorithm is on this slide. If it's a little bit hard to follow, like just, you can look these slides up later. But the point is, you basically take your numbers, color them into k-square random colors, find minimum for each color, and then among these k-square minima, you find k smallest numbers using some of the circuit from previous slide. And overall, this would be size n plus k square log k. So basically, for sufficiently small values of k, that's pretty much linear size. And the reason why this works is because if you color your numbers into k square colors, then with high probability, all your k truly smallest numbers will be colored in different colors. So you will not rule them out when you compute minimum for each color. So it's very easy. It also was very useful. So specifically, this allowed us to improve concrete running times by orders of magnitude, by shaving this log k factor. basically, the reason why I bring up this example, first of all, again, because it's self-contained, but also because this idea of coloring into like k-square colors, again, it's used everywhere in streaming. So when you have some big range, maybe you kind of like compress your range by doing some sort of hashing, and then for small range, you do something else. So basically, this allowed transfer. So this is a case study of like example where you do some technique transfer from one field to another, and also an example of somewhat non-standard computational model, which goes beyond RAM machine, which required, where even like very simple basic problems like choosing k smallest numbers in an array still required some kind of novel trick. Okay, so that's it for technical topics. I just wanted to give a couple of remarks before I conclude. Just if you are thinking about going into doing research, maybe specifically doing algorithms, but not necessarily, then the first thing you might ask, like, do you actually need to get PhD, right, in computer science in this case? And the answer is technically no, you don't have to, right? No one prevents you from just, not getting PhD, but like, sitting at home, inventing new algorithms for the problems, publishing them, and making everyone happy, including yourself. But in practice, that doesn't work. So you like, again, it's not impossible. There are some examples of people without formal degree making like very important contributions. But nevertheless, it's much easier to enter the field if you work for like 5 years with someone who already is like established expert in the field. So they would show you the ropes. They would show you how to think about these things. They would suggest some problems to work on. So I highly, highly, highly recommend getting PhD if you want to do any serious research, including algorithms. But again, that applies much more broadly, any area of computer science. And again, I don't want to like say specific country names here, but let me also say that research infrastructure, it heavily depends on the country where you are. So both for PhD and for specific research work that you hope to do, think carefully, like which countries are most suitable for research that you might want to do, which countries are maybe slightly less suitable. And a couple of other comments. Again, maybe that's one difference between research and competitive programming, is that research is much less objective than competitive programming. Competitive programming, you have some well-defined problems, you solve them, so you get your like plus in the monitor, and there is nothing subjective here, right? But research is much more subjective in the sense that, not only you need to solve a problem, you need to convince other people that this was a worthy problem to solve to start with. So one obvious way to do it is to just solve some open problem that other people left for you. I personally find it maybe a little bit like less inspiring than coming up with some new cool problem and convince other people that, this is a good thing to work on. But, both paths are possible. So basically, my point is that it's much more subjective. So, like, plan accordingly. And another thing, it's kind of related to the previous thing I said, it's community. So big part of having fun while doing research is being part of the community. In general, it's a really great community of people. Again, it depends what specific area. And in some areas, maybe the community is not so great then as in others. But in general, I think this is a serious perk of doing research, like being part of the community of researchers and just do things together. In particular, like research in algorithms ends up being very collaborative. So personally, I don't have any papers where it's only me as an author. So all my papers are with other people. Sometimes, not very often, but sometimes it's even like, relatively speaking, lots of people. And usually it happens that like everyone made some meaningful contribution. So your overall algorithm is a result of like a bunch of people working together. But in that sense, you are well prepared for that. Again, you are supposed to work as a team. Okay, and that concludes my talk. If you have any questions, you can ask me either now, or you can find me on like social networks, or send me an email, or like, send me some Telegram. I'm not really hiding. But yeah, if you have any immediate questions now, you can ask them.
Any questions?
Yes.
I think we have one question from here.
On the top K problem, can you just have a probabilistic data structure that kind of resembles a Bloom filter, and you scan all the lists and just put them in that data structure? And then that will give you the distinct number of distincts?
I mean, what are we trying to accomplish, I think? Let's talk offline. It's like, it's a great question, but I think we need to understand what we're trying to do there.
Okay.
But I think something should be possible, yeah.
Anyone else? Well, we have time. Oh, here. One more question, and then I will invite everyone to talk offline, because Ilya has arrived and he will be staying with us during the entire event.
Thanks for a great talk. I have a question. I think you, with your experience, maybe can answer this. So nowadays, machine learning is maybe the most popular field. And
sorry, can you speak up a little bit? I really can't hear you well.
okay, sorry. So nowadays, machine learning has a lot of problems, and a lot of people work there. But basically, they do not know the structure of the problem. But in algorithm research, it's different. You know the structure, and you can try to use it to optimize. And I believe some of your research also try to combine these areas. And what do you think? What are the main problems? How to combine these fields? What people need to study, maybe in university, to like solve it?
So the question was, how can you combine algorithms and machine learning, very roughly speaking, right? Yeah, there are many ways to combine it, and there are, like, again, let me give a brief answer so that, you know, we're not out of time. So one way is to just, you know, use algorithms to, for example, speed up some model training or model inference, and there has been lots of progress here. Like, for example, people use sketching techniques to compress the models, compress the machine learning models so that they become smaller and you can do inference more efficiently. There is also other relatively recent field where, you know, so for example, we all learn how to design good algorithms, but maybe we can use machine learning to design good algorithms for us. So maybe we can learn the best algorithm for the problem. Maybe we can learn the best sorting algorithm. Maybe we can learn the best algorithm for some other problem that you care about. And if done carefully, actually it turns out that you can achieve some progress here. Usually you do not obtain better worst case bounds, but you kind of, machine learning usually helps you to tailor your algorithm to specific input distributions that you might want to care about. And what to study in the university, again, it's a great question. Maybe let's talk offline about it. So, thanks.
Thank you so much. So, I see that a lot of people are following us on ICPC Live, and I would like to say hello to everyone. And for those who are here, we have an amazing panel discussion right now. We invited a lot of ICPC alumni, and we would like you to learn from their experience about what are the different career paths. For you being the current ICPC participants, what opportunities you can find within academia, within industry, or creating your own startup. So we are just taking a few minutes to prepare the stage, but please stay here because it will only take a couple of minutes. And I wanted to remind you about some guests who could not attend this event. You know, we're all living in this difficult pandemic time. It's very special that we could meet here, but I would also like to introduce someone who couldn't make it to Moscow, Dmitry Maslov. Maybe some of you have met him already. Dmitry has created a virtual room and he has office hours. Today it will be actually right after the lecture between the noon and the 2 p.m. Moscow time. Dmitry is the he's the CTO of IBM Quantum. So if you want to learn more about quantum computing, this is the right person to talk to, and you also have his personal email address, so you'll be able to reach out and ask any questions you have. And while we're preparing the stage, I would like to hear a little bit from you guys. So, because you traveled all over the world, so please raise the hands. Who is in Moscow for the first time? Whoa, that's quite a good number. So, I would like to learn about your experience. So let's see who can share it with us first, or who wants to share it with us first. Maybe you've discovered something that you would like to share with other participants. What about you? It's not the first time. So who was for the first time? Jelani, I guess you are here for the first time.
I just landed last night, so I don't have a lot to say yet. Although we went to see ballet yesterday evening, it was pretty nice at the Bolshoi Theater.
Nice. Anyone else? What would you recommend to your friends to see around? Did you have time to go to the tours? You guys? Where are you from, first of all?
We're from Bangladesh. Yes.
And it's your first time in Russia and in Moscow?
Yes.
So how is it going so far? What's the main impression that you've got from the city? And what would you like to share with your friends when you go back to your country?
It was very nice. We went to Kremlin yesterday and we saw and experienced everything actually. It was very nice.
The history of the big bell in Kremlin is so nice. I'll recommend my friends when I return back to my country. In their leisure time, they should go to Moscow and visit its historical places, its traffic systems, and all of the city is so nice. I enjoyed. Thanks.
Okay, well, you know that you are very warmly welcomed. We have volunteers here wearing yellow t-shirts, so if you want to learn something about Moscow, if you need any help, you can always find the volunteers. And again, we will be starting now. I would like to invite Jelani to the stage to start introducing the guests, and I would like all the guests to get ready. So, first of all, we will start with the introduction of Jelani himself. And guys, if you have time, please come and see Jelani. He is now the chair of the ICPC Alumni. And we are running a lot of lectures throughout the year. So basically every month we have a new lecture. And Jelani, he is the former coach of, well, we don't really have former coaches in the ICPC. But Jelani was coaching the teams at Stanford and, at Harvard? MIT and Harvard, sorry. And currently he's at Berkeley. And Jelani, thank you so much for launching these initiatives. We've heard some feedback from the community about this alumni talk, so maybe you can share something about it while we're waiting for the rest of the speakers.
Hi, everyone. Yes, I'm Jelani Nelson. I'm a professor at UC Berkeley in computer science. I was a co-coach of the MIT team, I guess, from 2006 to 2009 or something like that. And then eventually I moved to Harvard. I was a professor at Harvard, and I was a co-coach there for a while as well. Yeah, I mean, I feel like I myself benefited a lot from the programming competition community. Let me take this off. And I'm a researcher. I do research in theoretical computer science and algorithms, much like Ilya. And I thought the ICPC World Finals is a great time where many people, young people who love algorithms, are coming in one place together. And wouldn't it be nice to showcase modern algorithms research, and not just research, but also just trajectories of other ICPC alumni. So,
and we are ready to start. And
yes,
we brought many of them to Moscow. Again, we are welcoming all of you to the upcoming World Finals as the alumni, but right now you'll meet some of the stars. So I would like to call on the stage Pavel Gavrichovsky. Let's give a round of applause. Pavel is the ICPC coach. He is doctor assistant professor of University of Wrocław. So Pavel made it here from Poland. Please, welcome. Maybe you can put it here, right? Then I would like to welcome Klara Horachkova. Klara is the ICPC alumni, currently working at Google Zurich as a software engineer. The other person that I would like to call, and many of you know him, is Roman Yelizarov, the legendary champion of the ICPC, the head of the ICPC Live, and the chief judge at the ICPC NERC, and also the lead for JetBrains Kotlin team. If you didn't meet Roman yet, you'll have a chance to talk to him after this talk. The next speaker is Viktor Shaburov. Viktor is a serial entrepreneur, investor, and one of the founders of several startups, including alumni from the ICPC, and those companies include AI Factory, Luxury, Handster, and SPB Software. And currently, Victor is also serving as the director at Snapchat. So the next guest is Ahmed Mohamed Kamel. Let's welcome Ahmed. He is the former coach and the head of the scientific committee of Egyptian Olympiad in informatics. And currently, Ahmed is living in Amsterdam and serving as a senior developer at Booking.com. So we can't wait to hear about that. And our next speaker is Nikita Shamgunov. Let's welcome Nikita. Nikita is currently serving as the partner at Kosla Ventures, and Nikita is the founder and CSO of Single Store, which is the current MSQL. So if I forgot anything, please add it. I know that some of you have prepared some wonderful slides introducing what you guys are doing, and we're ready to go. And thanks for being here.
Okay, thanks a lot, Veronica. And so let's get started. I thought maybe the first thing, and each of you has a microphone near your chair. Maybe we could just go in order. Just quickly introduce yourselves and say, what your connection to ICPC and what you're doing now.
Yeah, it's like, I'm not sure if it's on. Is it on? Yeah, I think so. Okay. Can I get my slides to show up?
Yeah, can we get the slides for Pavel Gavrilovsky? Or maybe,
Okay, so hi, I'm Pavel, and I'm University of Wrocław, and just in case you're not sure where is that, I'm not sure how to, okay, so it's in Poland, in southwest of Poland, and I studied at the Institute of Computer Science there. So this is the new building. I had to go to the old one. I'm not showing you how it looked like because it was not so nice. And when I was doing my master's degree, our team went to the finals. It was in 2005 in Shanghai. I hope you can still recognize me on the picture. And we got the 5th place, which was great because that was the first time our team, our university went to the finals. Yeah, so it was a very big achievement for us. And after that, I did my PhD on some string algorithms at University of Wrocław. And after that, I did a bunch of postdocs at Saarbrücken, University of Warsaw, and University of Haifa. And I was still kind of involved in doing some ICPC stuff while I was away. But then in 2017, I went back to Wrocław, and I became more involved. So in 2019, we had a team in Porto that I co-coached, and we managed to get the 6th place, so it was again great. And we have a team in Moscow now, but well, we don't know yet what's going to happen, yeah? And I'm a researcher. I'm mostly interested in algorithms and data structures, so algorithms on strings, algorithms on planar graphs, and data structures. Yeah, that's it.
Thank you. Please, let's continue.
My name is Clara. Okay. Hi, my name is Clara. I studied at the Czech Technical University in Prague. I studied there computer science, and between 2014 and 2017, I participated in ICPC. While I did my master's, I did an internship at Google. I also work as a research assistant, and after graduating, I went to work in Google for full time. And I'm from Czech Republic, but for the job, I moved to Switzerland.
Hello, my name is Roman Yelazarov, and I actually have a question for the audience first. So how many of you here have come to ICPC from your interest in school? How many of you were in International Olympiads in informatics or like prior competition? Just raise your hand. Who is here because of IOI? How many people? Yeah, I see a bunch of heads, and that's interesting that for me, for example, I went to, when I was an IOA competitor in school, that was my thing in school. And when I went to university to study, I thought, that's it, you know, sports program is over. I mean, now I study to work in the future, etc. And lo and behold, I was a lucky one because that's, as I was a freshman, our university got a award that there is this competition, you know, called ICPC, and we can participate. And that was amazing, you know, I didn't imagine this, it wasn't planned for. And not surprisingly, so we were like the first team from our university to compete. We were one of the first teams from Russia to ever make it to the finals. And that's kind of kept me then in this experience of like not expecting it, but getting to the ICPC community got me glued to it. So I since then, you know, having finished competitions, I've started organizing, and I'm a chief judge in our regional since then. But I've, unlike some other people who you heard here, I toyed a bit with idea to have an academic career, but then went to industry, and kind of industry consumed me after that. And I don't have any regrets for that. And actually, from my experience, I mean, if you come talk to me later, my experience is working in industry is actually a really positive one, and I'm kind of an example where a person with ICPC skills can get lots of satisfaction of life and work while working solving challenging problems in industry.
Hi everybody. So can we? Yeah, thank you. So can we go to the next slide? So my name is Viktor Sheberov. I'm investing in ICPC teams, and we have good track of record. Oh, all right. I can do it myself. So anybody of you used Snapchat face filters? If yes, could you raise the hand? Thank you. So that was developed by ICPC team, which we invested, and I will shortly tell what happened to the guys in whom we invested, right? So in this case, it was Ukrainian team. The main guy was Yuri Monastyrshin. His team ranked 38 in the world finals, and he made a very successful startup with our help, and we sold it for 150 million to Snapchat. He also became one of the youngest directors at Snapchat, directors of engineering. He became at the age of 24, and that's an example how you make the fastest possible career in a big corporation. You need to build startup and sell to that company, so you make both money and you grow in your career. So how do I? Yeah. So another guy in whom we invested was Vasily Filipov. He was number 8 in the ICPC finals. I guess he got bronze. And the company was called SPB Software. It was acquired by Yandex for 38 million. And he is currently running a new startup about education in VR. Another guy, he was not ICPC finalist, but he was IMO finalist, silver medal. And we built an app store company, sold it to Opera together. He is now, he returned back to science, basically. So he decided entrepreneurship was too much. He wants be back in the scientific world. And another guy, his name is Alexander Mashrabov. He was finalist, ranked 38, and we built together a deepfake startup called AI Factory, and we actually we sold it again to fails with one idea. They can start with another idea. And for example, in the last startup, they did 3 pivots. So they switched from different tree ideas. And that's why we love ICPC guys. I also was Olympiad participant, but it was in mathematics before. Thank you. And that's my contacts if you need them. Thank you very much.
Yeah, hi everyone. I'm Ahmed Kamel. I used to participate in IOI before ICPC, so I'm one of those that Roman asked it for. Yeah, so I joined university for Arab Academy for Science and Technology in Alexandria in Egypt. I graduated for computer engineering, and then after that, I joined Booking.com in 2016. So I've been working there for 5 years. During my college, I participated in ICPC. So I was a world finalist in 2013, and we got the champion of Africa and Middle East during that time. Yeah, I used to coach as well, like my university students for Egypt during these 5 years, and participated in judging national competitions and yeah, in different countries. Yeah, that's it for me. Currently, I work for Booking as a senior software engineer in rewards and incentives track. It's a marketing department where we incentivize people to book more, or actually rewarding them for booking with us. So that's my field. And we maintain our infrastructure and services, microservices for that.
Hello, my name is Nikita. I have a bronze medal in ICPC from way back in the day. Since then, I worked for some big companies like Microsoft and Facebook, which is not a bad thing, but I think you can do better. After that, I started a company called MemSQL. It became Single Store. It's $1 billion company. I was fortunate enough to be able to convince some of my ICPC friends to come join. They did. We built the company together. It's worth over $1 billion. Since then, some of those friends left the company, started their companies. There are multiple $1 billion companies that are started from MemSQL alums now, and hopefully they also hired a whole bunch of their ICPC friends. And hopefully those companies will also have alums, which will start their companies. They will hire their ICPC friends, and they will be also wildly successful. Victor can give those companies money. We can give those companies money as well. I think it's an absolutely unlimited amount of technology and companies that can be built. So there's absolutely no such thing as a monitor for the world. You can build as much as you want and as much as you can. And it's exciting, it's fantastic. And come to Victor, come to me, and we will give you money to do so, because sometimes company building takes money.
All right, great. Good. Thank you, everybody, for introducing yourself. I have a few questions just to start us off with, and then maybe after we do those, we'll leave some time for questions from the audience. So my first question is, relating the ICPC to what you do now. So programming competitions like the ICPC, it's testing for a very specific skill set, mastery of some particular subset of algorithms, the ability to write, correct code, efficient code to solve problems that use those algorithmic techniques, in a limited amount of time. I'm curious to know, in what you do now in your careers, how has that skill or other skills that you've learned from your ICPC days helped?
Okay, so I think I definitely got interested in research because of programming competitions. So, in a competition you have 5 hours, so it's a fixed time frame. The problem cannot be too difficult, but once in a while you see something and there is more to it. So you start to read, and that's how I got interested in learning more about algorithms and data structures. So for sure it got me started. I mean, it's a different game, as Ilya mentioned. I mean, you don't really know what's the goal. I mean, you have to define the goal for yourself in research. So it's slightly different and can be frustrating at times because you don't really know what's the answer and what's the problem, and you have to define it yourself. But for sure, it's kind of something that you can start with, and it gets you interested in doing research, possibly. So, I mean, some of the knowledge that you get after those competitions is for sure helpful later in the academic career, but I mean, you have to learn more. I mean, the repertoire of tricks and techniques that you know it's much wider, so you do need to spend some time, but it's something that you can start with, and for sure it helps. And I think the other thing that helps is that many people in academia that I met, I mean, for sure they have heard about ICPC, and quite a few did something related, either coaching or participants. So it's something that you can talk to people about, and I think it's great.
So the real-life problems are apparently a bit different from the things we are solving in ICPC, but generally, for example, we are working with huge data, so that's definitely worth to know some efficient algorithms. And what I think is important is that when doing contests, you get a sense for the detail, and you get used to test what you are doing really well. And I think these are the things you can use also in the real world.
So in my career, I've actually hired lots of people to teams in different companies I worked in, and both people with sports programming experience and without it. So I can share some my experience from this side, not what helped me personally, what I saw in other people that helped them, the people who are sports programming or IOI or ICPC contestants, what helped them then build a career. And this is not to say that you have to have programming experience, like to have a good job or a great career, but when I look at former ICPC contestants, I see three things that really help them in future industrial career. One thing is they learn how to learn. Like when you prepare for a contest like ICPC, you have to learn a lot. You have to practice a lot. That takes a lot of grit, a lot of persistence, and this kind of a skill you learn while practicing, which helps you immensely in later life, regardless of what you do later in life. Like if you go work somewhere, that very helpful skill, because whatever job you get, you'll have to learn again. It's not like you finish university and now you apply your knowledge. This never happens. Like you have to learn at your job, like from very start. And like knowing how to learn, how to arrange that, that's a very helpful skill you practice when you prepare for ICPC. The second very important quality that people, ICPC contestants have is their ability to work under pressure. You can't become a good ICPC contestant if you can't work under pressure, because here is your really limited time, and deadlines and limited time happens elsewhere. Even in academic research, you know, even though like you can research for years, there are still deadlines for publishing papers, etc. And you have to be able to work under the pressure, and that's what ICPC teaches you really well. And I mean, it's hard to pick the third thing, but what I think great for ICPC in particular, and that's very particular ICPC feature, is that ICPC is a team competition where you have to actually work in a team. And that puts it aside from many other sports programming competition out there, and this really gets you to practice skill working as a team. That's really important. Like none of the major problems in this world are solved by a single person. Like most of breakthrough in industry and business happen as a result of a teamwork, and practicing this teamwork, like learning how to work in a team, that's what puts ICPC contestants aside and give them an edge in life. Thank you.
So basically, I can tell why we like ICPC guys, because they are very aggressive and very fast. And they were maybe number 30 in this competition, but they were competing against everyone in the world. And if you give them very narrow area, like face tracking, they figure out that they will probably be number one. And they start pushing very aggressively. And also they understand that you need to use every chance to win. Like sometimes 30 seconds is difference between like number one, like between gold and silver, right? So time is very important, and I can also give you example like how aggressive sometimes team can be. We had to, when we did Luxury, which is face filters, right? We had to fly to meet Samsung before the acquisition. And you know, Samsung is a big corporation. How to explain them what we do? And the guys came up with the idea to rent billboards in front of every entrance to Samsung offices in Suwon. And that's not expensive because it's somewhere like in suburbs. And they rented like Luxury with iPhone, on every entrance. And when I arrived, every damn director and VP knew about Luxury and tested it. And the meetings went amazingly well. So that's what we like about ICPC team, being extremely fast and extremely aggressive. Thank you.
Yeah, for me, I guess teamwork is one of the skills that we have learned during ICPC under pressure. So I believe this has given me like some kind of soft skills that enabled me to work for a bigger company and wider variety of people and project as well. So yeah, and also different titles. So I think, generally speaking, I think my life has been easier just because of being in ICPC and IOI. And this like also, yeah, problem solving skills is kind of in everyday life, but it's not like exactly how we face it every day in every competition in ICPC, but it's like from a different perspective. So we still solve problems. Yeah.
I guess the question is really, what are the superpowers of ICPC alums? And you know, other people already talked about some. I want to add the one more, which is quality, right? You know, we all trained to think about corner cases, and in certain parts of technology, in my part, for example, databases, you kind of really need to think about corner cases and quality. And so we got really lucky with that. But then there's one more superpower, I think, that the other folks haven't mentioned, and that is the community. And the fact is that if you are an ICPC contestant, you have a whole bunch of friends who are also ICPC contestants. And then as your career progresses, as you build new things, if you want to start a company or join a big company or do whatever you want, you have your friends you can reach out to, and you can start solving problems together, building things together. And I would like to please ask you not to ignore that part of your superpower, because you absolutely do have it. So don't miss out on that.
All right, thank you. And maybe I want to go a little bit deeper into something that several of you already mentioned, which is, you know, the networking aspect of ICPC, right? Finding people to hire or to work with. You know, there is a big community, even, you know, the programming contest community at large, even larger than ICPC. You know, months before the World Finals happens, you go on Codeforces and you see posts that try to list everyone and, you know, what's their handle, and people know each other already from other contests. Can you say a little bit more, each of you, about, I guess, how the kind of the community has, you know, impacted your life, the programming contest community, and the benefits of that?
So it's indeed a very nice and kind of large community, and whenever I meet someone at a conference, I mean, this is something you can ask about, and in most cases they would have heard or participated or coached a team. So it's always some way to connect to people. That's one aspect. The other aspect is that when you look at all those online, I mean, now it's Codeforces, but before that it was Top Coder, and you could really read about very interesting things and learn about new techniques, new tricks, new algorithms there. So I think it was like a really great resource, and it's still a great resource. You ask a question, and there's a chance that someone who really worked on in the area or on something similar would reply. I think that's really wonderful.
So that's definitely good when you meet some other people on an event like this, and then you go to some other place and you find out that you already know some people there. So it's great that to see familiar faces around. And one other thing that is really great is the motivation, because when you see all around people that are very motivated in the things they are doing, it doesn't actually really matter what is their field of interest, but as you can see that they are really putting a lot of work into their goals, it also motivates you to achieve more.
So in my life in particular, ICPC community has had a great impact. So the first company I founded with my friends was actually, we are mostly founded by ICPC alumni, and we've employed a lot of ICPC alumni, and we had great success in the niche the company was working. And again, that's because we work with like-minded people who have similar approaches to problem solving and to teamwork. And then 5 years ago, I've joined JetBrains, and it was again not an accident, because JetBrains CEO Max Shafirov is actually a former Moscow State University coach, so he's also an ICPC alum, and that's the conversation we had with him motivated me to join the company, because I knew that if a company's CEO is the person I know has a like-minded approach and I can trust, and that's really makes a big difference when you pick a place or direction where you work in. So, and if I can give an advice here to contestants here, whenever you choose where to work, don't just look at the company, especially if the company is big. Always look at who are the people you're going to work with, what's their background. And my personal experience and experience of some other people I've talked to shows that you'd be way safer with ICPC community since they're usually very motivated people, and together you can build really great things.
So, the ICPC guys, they basically understand that to win, you have to have superstars in your team. So everybody should be amazing. And that's kind of, they bring to the business world, so they hire only the best guys into their teams. And I had the example that we helped them also to find superstar marketing directors, superstar salespeople. And the example was that at the luxury time, when we we did pre-launch with Kickstarter, and we hired a marketing director a long time before the launch, and they were not happy, and they, as a result, changed 5 marketing directors. And number 5, she was an amazing woman who did some miracles, and with her, the company become number 1 on App Store in 5 countries, top 10 worldwide. So the example is they're not happy with mediocre people. They want superstars, and they are not happy until everybody in the team is a superstar. Thank you.
Yeah, for me, I feel it's more of, so the community helped is that I see in every country and every company I have friends or connections, which makes me feel belonged, even if it's another company. So I feel like the community helped in putting me in this position, and also, at the same time, we still kind of refer each other to other companies and stuff like that. So it's like we are working to improve the tech industry. It's not like we are working for one company at the same time. But yeah, I feel ICPC is not over when I left ICPC. It's still kind of happening. And one fun fact is that we still actually, in my company, we still participate in sub-regional of ICPC in Netherlands. So the Benelux, it's Belgium, the Netherlands, and Luxembourg. So there is some section for company league, and yeah, it's still happening. So I don't feel like a nostalgic to this era, because yeah, like every day we still have it.
Cool. Yeah, the question was what's the impact of ICPC community on my life? Well, of course, without ICPC put me on the map. So I would have not been in Silicon Valley, would have not built companies without ICPC, and without ICPC alums who were my friends. Some of the other folks talked about being safe, going to somewhere, understanding what are the people and who are the people you'll be working with, and that's absolutely true. Anywhere you go and anything you do, I think you need to understand that there's this notion of risk, and risk is something that is so innate to everything that you're doing, because we live in the probabilistic world, basically, right? You make decisions, you're going to go and do, and you can do A or B or C or D. So what I can tell you is, if you go and catch me offline, is what are the possible choices, right? So everybody knows that you can do A, B, and C, but maybe you can also do D, E, and F. And those things are, maybe not so obvious and may look a lot riskier than doing A or B or C. But actually, whatever you're doing, there is a risk to that. And then there is a risk that you take in a calculated way. You deliberately go and take that risk. And then once you decided what is the high order bit, what is the most important thing, then you actually start thinking about how to de-risk the rest. And that's when you start doing, and let's say you chose to do, C with your life. And that's a big risk, right? Because all your life, you only have one life, right? So you're putting all your life eggs in one basket. Then you can de-risk some of that stuff. And that is doing whatever you decided to do with your friends from the ICPC community. I assume that it's mostly technology because we're technology people. And it's just easier, it's better and culturally more cohesive to work on something together with your ICPC alums.
All right, thanks everyone. We only have about 12 minutes left, so I want to maybe open up questions to the audience, either to the general panel or if you have questions for any specific panelist or panelists. Anyone, questions? Let me just stand up if you have a...
What's your name?
Hello, I'm Manuel. I have a question. I think it's an open question to everyone who wants to answer. So in your experience, how well it translates the abilities that you learn here on real industry? I mean, because here we work on small scripts and we don't have the cleanest way to write code. And all these abilities that are very specialized to problem solving and small scripts. In your experience, how well it translates that to the industry when you have to work on large code bases, on bigger teams to be able to consume APIs and all those things? Those are kind of very different abilities.
Yeah, I can try to answer that. In my experience, it translates really well. Like from most of the ICPC contestants that I saw working in large companies it doesn't mean like you finish ICPC and you start performing really well in industry and large code base and with large teams. But you have to start with something. ICPC gives you basics you need to work in small teams on small code, producing high quality code. And that's actually Ilya what mentioned. The quality is what you also train to think of edge cases and think about quality code when you are in ICPC, and that translates extremely well in your later. Of course, there will be lots of new things you'll have to learn to just, and there will be a challenge of you learning how to work in a larger team. There will be a challenge in learning how to work with the culture. You'll have to learn that too, in addition to what you have learned in ICPC. But from my experience, if you mastered ICPC, if you are the world finalist, you made it to the world finals, means you mastered working in small teams and mastered working on a smaller size problem. You have what it takes also to, in a year or two, to make a further step and learn how to work on large problems in large teams, and you'll be doing just great.
Just want to add a couple 2 cents here. So there's always that talk for some reason that, oh, well, IOI, ICPC people are maybe good in solving these little problems, but yada, yada, yada. And actually, it's all bullshit. The only one ingredient that ICPC alumni need to have to be very, very successful in the industry is hard work, right? If you don't have that, then no good things are going to happen. But once you have hard work, the fact that you are in the world final for ICPC actually means a lot. And so there's no such thing as, oh, they were good at ICPC, but, and actually it's amazing that you guys are in the world finals. It takes an incredible amount of skill and hard work to get there, and that positions you incredibly well to do a lot of great things, and you are positioned so much better than many other people who don't have that, neither on their resume nor on their skill set.
So basically, I would add from my side that we really love ICPC teams to focus on unsolved problems. Like there is some kind of unsolved problems, like there was, for example, this real-time face tracking, and then they're able really to focus, solve it, and make a really nice startup about it. I would say that if it's a like solved, well-known, like some banking solution or business solution, they would be bored and probably not the right team for that. But if it's something really which nobody ever solved in their life, this team has no fear to approach it. Others have fear. Like ICPC guys have no fear. They approach unsolved problems and try to solve it. That's why we love them. Thank you.
Any more questions?
Someone had a question here? Can you raise your hand?
Hello, my name is Vladislav. Can you comment statements that ICPC talents generates not supportable, maybe not a good code, and it's usually difficult to interact with that guys in enterprise code. Enterprise, I don't know.
Sorry, so what was the question? That some people say that it's difficult to interact with the people?
Yes, it's difficult to interact with, I don't know, ICPC talents guys. So usually they aim to fast solve a problem, not generate some enterprise code. Can you comment this statement?
Yeah, I can comment. That's bullshit. Because, I mean, it's much easier to take a person trained ICPC and teach them writing understandable, clear, nice code for industry, then take person who can do this, who can do ICPC, and teach them writing correct code that cares for all their corner cases. Like, it works way better the other way. Like, if you already train ICPC, like, it doesn't mean you immediately get writing great code and good work in big team, but, I mean, they can learn quickly. One of the superpowers, as they said, of ICPC contestants and the finalists, they can learn really fast.
Yeah, I would like to add to that. So usually people, once you enter a new company, you will need some kind of soft skills to like deal with product managers, different types of roles. And yeah, by time you will actually gain this. It's not that easy and at first, but it will like just evolve. Normally, it's not like totally different world. It's still actually solve a problem, but in a bigger project, there has to be some patience because projects are not like gonna finish in 5 hours. It's like they're gonna take maybe months, years. So it depends on of course, where you are working, but generally speaking, it's not like totally different world. It's still problem solving in a different form. That's it.
Any other questions?
Hello, it's me again. This question is more for you that you have a lot of experience training, but if anyone else has experience also training teams, that also welcome the answer. So we are a small university in Mexico trying to generate top quality teams. So what will be your advice to the trainers and to the competitors to keep growing and next year's bring more teams to this competition?
So we can also only try to help a little bit. I mean, it needs to be the teams themselves who want to practice and invest. I mean, it's an investment of time. I mean, you need like 2-3 years, I think, to really know all the tricks that you need to participate. So it's an investment. And we can try to help a little bit, give some advice and create a nice environment. So at my university, we have classes in computer programming. But it's not me teaching. I mean, it's the competitors themselves talking to each other. I just try to moderate discussion and try to create like an environment, and we all do. It's not just me at the University of Wrocław doing that. And we try to get as many people as possible getting involved, because I mean, not everyone will be interested in spending 2-3 years. So we try to have a large pool of people who do this kind of activities. And we actually started in high school. So we have the Olympiad in informatics, and many people in different high schools in my city, they attend classes that are being taught by people from the university, by students or by faculty, and then some of them come to study computer science with us, and then hopefully they will become interested in ICPC and continue. So it's a long process, and I mean, but we try to make it so that everyone tries a little bit, and then some people will decide that this is that they really like, and then they will continue and spend more time on that. So that's my advice.
Anyone else want to comment on that? Okay. If any other, well, I guess we have about 2.5 minutes left. Maybe one last question. Time for one last question. If not, maybe I'll ask you a quick question. You know, we're all now many years out from graduating from undergrad. If you could go back to your former self and tell yourself kind of just one line of useful advice you wish someone had told you, do you have any advice that you want to pass on to the youth? Okay, we can go in any order.
Yeah, I would go to startups a lot sooner. Something might be controversial. I wouldn't do a PhD. I did a PhD, and now I'm not sure if I would have done PhD, especially knowing and having access to all of the resources that you guys have today. I wouldn't say I had those resources back in the day. Now, it was at ITMO, it was fantastic, but still it's, sets you back for, 5 years in your life. And then you have like, your kids are born later by 5 years and stuff like that. And the other kind of advice is to really understand something that venture people actually understand, and that goes back to risk. That's some things that you do, and especially you do when you're young. Your risk equation is very different, and sometimes you do something that has certain amount of downside, that's your risk, but then certain amount of upside, and certain things that you can do have unlimited upside. And when you're young, you want to do those. So that's what I would have started to do a lot sooner in my life.
Yeah, I would say it's very basic advice, but I think everybody needs to do it, which is if you are actually interested in the tech industry, then try to join more internships during your study. This would actually enable you to solve real-world problems and be into the practical field than actually just problem solving and using algorithms every day. So yeah, just do that more. For me, I only did one, which I think I kind of regret. So yeah, that's it.
So my advice to myself is set bigger goals. That's very important advice, you know. And it's funny, maybe I was a stupid guy, but like when I was a student, my goal was, hey, I need to become like a millionaire by the age of 30. And of course I become, but that's, if I would set a goal to become a billionaire, it would be probably also possible. Because it's same time, it's approximately the same time to build, if you have a goal to build a company that's 10 million, it's probably same time as if you have a goal to build a company which is 10 billion. So set bigger goals and don't fall into corporate world. Because if you go to work for a big company as a software developer, you blink your eyes and then you have wife, kids, mortgage for the house, and you can't live for startup world. You know, go into startup world as early as you can. Thank you.
So my advice, I actually second Nikita, just when you're young, you know, try lots of different things, learn different things, learn fundamental. You'll get your life focused on a single few things later in life. But while you're young, just do everything, like try different things, take all the internship opportunities, and don't pass on opportunities. Like if there's something scary or challenging opportunity before your eyes, just take it. I mean, that's when you're young, that's the time to risk and do the most challenging things. You can catch them all as they go by.
So my advice would be to keep a good work and life balance, because sometimes it might be tempting that you want to solve some problem, so you would like to be by your computer for a long time, but it's important to take some time to get out of a computer and, for example, do some sport or your other hobby. Yeah. There are also some other things apart from just competitions.
So my advice is that, I mean, you can choose what you want to do. You can go to industry, you can go to a big company, or you can do some research. And my advice is just choose what you like. I mean, there are different factors, but you should choose what you like and what gives you most satisfaction, I guess. And it's still time to try something and switch, so.
One more. Don't do what you hate.
Yeah. I mean, maybe
Life's too short.
I feel compelled to add my 2 cents just to provide some counterbalance, because I know, Nikita, you said, don't do the PhD, or at least you didn't feel like you personally wouldn't have wanted it done the PhD.
That's right. This is not exactly for everybody, but this is my personal suggestion to myself.
Yes. So I mean, I personally am quite glad I did the PhD. Maybe you too. You're in academia as well. Depending on what you want to do, right? If you want to build products that millions of people use, then maybe going for the PhD is not necessary. It depends exactly on what kinds of products, but if you're really passionate about pushing the frontier of human knowledge and doing original research and discovering things that maybe not a product that millions of people will use, but knowledge that millions of people will learn when they study computer science in school, right? And you help develop that could also be something very powerful. So I think the PhD is also something very interesting. And by the way, I mean, there are people who do both, who do a PhD, are in academia, and also have impact in industry. So I look at some of my colleagues at the university who are now billionaires because their research led into companies that they founded, companies like Databricks, for example, which was co-founded by Mate Zaharia, who was an ICPC alum. So there are people who do both, right, who do original research and then translate that research into industry later. So that is a pathway. Anyway, I think we are out of time. I want to thank all the panelists, and I especially want to thank Veronica, who helped a lot with starting this alumni speaker series, and also the panel. And also, I don't know if she's somewhere, Lydia. Is Lydia somewhere out there?
Lydia is the one who is doing the ICPC live broadcast. So
yes, okay.
She's currently busy streaming us, but let's give a big round of applause to her.
And also Lisa and Bill
speakers.
Thank you.
what I wanted to add, Jelani, as you said, we put a lot of efforts to bring this panel together, and I would encourage all of you, come talk to Jelani, and we hope to see you on the stage next year at the World Finals. And so just some small announcements, and again, thanks to all the panel participants, but it's not the end of the program for today. As for the planning for today, we have one more session on AI, and I would like to invite the guests here. We are just doing the small setup change. Then you will have lunch, and by the way, when you go to lunch, we also have some interesting materials that you'll be able to see there, and then you'll have some chill time. Weather is really nice today, so go and have a walk around, enjoy the sunny Moscow, and join the opening ceremony. So I am sure you're all looking forward, and those who are following us online, you will be able to follow us in real time online and assist to the ICPC 44th World Finals opening ceremony tonight. And right now, I would like to invite on the stage the head of AI team at Rosatom, Denis Larionov. Let's give a big round of applause. And Dmitry Ivanov, the machine learning engineer at Rosatom. So, Denis, Dmitry.